A warm welcome and a very good evening to all organizers, delegates, our respected resource person for today's session, and all participants of this program. Am I audible to everyone?
Yes, sir.
Thank you. Thank you so much. So, again, welcome to all. And I'm delighted to introduce the resource person for today's online session of the 1 month certificate program on effective research writing, Dr. Kalpana K. Mahajan, ma'am, a stalwart in the field of statistics and academia with a remarkable tenure spanning over 4 decades at Panjab University, Chandigarh. Ma'am has been a beacon of knowledge and leadership since her induction into the Department of Statistics in 1977-78. Her illustrious journey continued until her superannuation on August 4, 2021, during which she served in various capacities, notably as professor from 2001 to 2021. Dr. Kalpana Ma'am's contribution extend beyond the classroom as evidenced by her pivotal roles within the academic and administrative realms. She served as the coordinator of the UGC SAP DSA scheme from 2008 until its conclusion in March 2021. Demonstrating her commitment to advancing statistical education and research. Additionally, she held the position of chairperson, head of the Department of Statistics for 2 terms, further solidifying her influence within the academic community. Beyond her departmental duties, Kalpana Ma'am's dedication to fostering a safe and inclusive environment is evident through her tenure as a chairperson of the Committee Against Sexual Harassment and as a Dean of Student Welfare at Panjab University. Her leadership is in these roles underscore her advocacy for equity and social justice within academia. Her expertise is not confined to the walls of her university. She has actively contributed to shaping statistical education and research at a national level. Her membership in expert advisory committee for institutions such as UGC, IGNOU, and Kendriya Vidyalayas reflects her standing as a trusted authority in her field, and also on the panel of the number of selection committees of various universities and commissions such as PPSC, SSC, JKSSC. A prolific researcher, Dr. Kalpana Ma'am's interests span a wide area of statistical domains, including inference, Bayesian inference, multiple comparison procedures, income inequalities, and environmental statistics. Her scholarly output, comprising 6 co-authored books and 2 project reports, over 50 papers in leading international and national journals, guided 8 students to PhD and 16 to MPhil, stand as a testament to her academic rigor and intellectual curiosity. In addition to her research and teaching endeavors, ma'am is actively engaged in the scholarly discourse as a reviewer of prestigious journals such as American Mathematical Society and also some noted international journals such as Statistical Methodology, Communities in Statistics, Computational Statistics, etc. Ma'am's influence extends beyond academia into the realm of international collaboration as a knowledge dissemination. Her active participation in seminar, conferences, and workshops, both as an invited speaker and section chair, delivered over 200 lectures, presentations since 2011 on the Program Committee of Global Science and Technology Forum, which organizes international conferences, ORS. It organized more than 20 seminar conferences, workshops, including as a chair the International Conference of FIM 2012 underscore her dedication to fostering intellectual exchange and advancing statistical science on the global scale. So without taking too much time, I would like to invite ma'am to deliver the important topic of this 1 month journey of effective research writing, the inferential statistics, and the second topic of inferential statistics is parametric test. Please, ma'am, welcome, ma'am. Ma'am, please unmute yourself first.
Yeah, now is it is okay? Can you hear
Yes,
me?
yes, ma'am. Welcome, ma'am.
Okay, thank you so much. Thank you, Dr. Tiwari, for the kind words. I must congratulate Dr. Padam Singh and Dr. Pandey uh, and for the very good initiative of the institutes, microbiologist and Society India Institute of Applied Statistics. for these types of starting these types of courses. These are the need of the hour, and it's very good initiative rather. And I came to know that there is one more program running in the institute, so they are taking very pains to train the participants from the different fields. Okay, so let me come to my topic. This is inferential statistics, and particularly the parametric tests in this. Yes, luckily, I just attended the yesterday's lectures also. That was also the introduction of some testing of hypothesis. Some basic concepts were clear, but still, I'll try to revise all these things in short, and then we'll come to the parametric test, the basic parametric test. Okay. So these are the parametric tests, and there will be another lecture for the non-parametric tests also, as I can see from the program. So I'll tell you that what is the difference between these tests and in which situation we have to use which test. This is the basic problem with the researchers in different fields, that they are not able to understand, they are not able to check the assumptions for which test they should go. Okay, so we'll just start from the basics and then come to the different tests. Okay, and one more thing I will like to add, that if you face any type of problem, if you have any doubt in the topic itself, you can just interrupt me at that point only, and we can discuss. There is no problem, you can ask any question. Okay, and after the lecture again it is open for the discussion. And I can share my number also, and later at any stage, if you face any problem, you can just call me and discuss with me. Okay, so if we actually the estimation and testing of hypotheses or inferential statistics or the decision making, all these are just one and the same thing in the statistics. I'll tell you the different roles of the statistics in your field, and how to exploit these things in your research. Okay, so when it comes to the statistics, people, they have different type of feelings. They are just afraid of the using the statistics, but of course you know that we cannot survive without statistics. You just oh, this is again not working. Yeah, right. So you can see so many these types of quotations about the statistics, so many sayings about the statistics. And this is the very famous saying that there are three types of lies: lies, damn lies, and statistics. Or torture numbers and they will confess to anything. This is statistics is the grammar of science. This is by Carl Pearson, a renowned statistician. A single death is a tragedy, a million deaths is a statistics. Okay, 99% of all statistics only tell 49% of the story. These are the different sayings, but whether you appreciate the statistics or whether you criticize it, you cannot survive without statistics in today's world. Why? Because data is all pervasive. You talk about any discipline, you can find data everywhere, whether you go for sports, politics, economics, physics, chemistry, botany, national level, international level, space. You find data everywhere. Okay? So let us come to the data, because I will try to explain these concepts, these different tests by using a very basic data. Everybody who is doing research is having data with it. They just collect the data. Any method of collection of data may be used. It may be primary data, it may be secondary data, but data is with them. So I'll be just taking a simple data. Suppose I want to collect the data. My first thing will be, I will just report the gender of the person. So gender, employment status, then marital status, then family size, age, weight of father, and you can go on collecting more things on the more variables, because you see that these I think there was some lecture on the basics of statistics where it was this thing must be clear to you, that data can be on attributes and on variables. Data can be numerical and non-numerical. So here the first three figures, they are non-numerical. They are on attributes like gender, employment status means yes or no, marital status again yes and no. These are just attributes, and the rest of the things, they are variables. Number of family persons, this is a variable. Then family age of the person, then weight of the person, weight of the father, and all this. This is just a small example. You can collect the data on so many variables. These days so many softwares are available, and they can just store the data on thousands of variables. Okay, once you store the data, and then I'll tell you that how to frame the different hypotheses, how to exploit that data in different fields. Okay, this is the very basic data, and let us say we can go on continuing collecting this type of data from one group of persons. Let us say from your class, I have collected this type of data, and it will show like this. Now, how to use this data from around? Okay. Now, what is the basic purpose of statistics? Why everybody is using statistics? What is the basic purpose of statistics? The basic purpose of statistics is to find out or refer to or get at how we can talk about the data in minimum possible terms. You can see data is very, very, very large. How to talk about the data in minimum possible terms or words? And second thing is, what is the typical message hidden in the data? The only two things. If you talk about the statistics, we can say this, the twofold rule is there in the statistics. How to express the data in minimum possible terms, and what is the typical message hidden in the data? Means to describe, the descriptive part, and to infer. Description and inference. See, the whole statistics we can divide into two parts: describe the data, the descriptive statistics, and inferential statistics, right? So then the description and the inference can be about the individuals, about the institutes, about the processes, and about the phenomena. Only two things: description and inference. When it comes to the description part, statistics is playing twofold role. In the description, suppose we have this small data with us, we can just describe how many males are there, how many females are there, how many of them are married, and what is the averages, like that. You can get the answers of these questions, you can describe these things. Okay, and when it comes to the inference part, then can we say that more male than female attend classes? Can we make such type of decision? Can we make such type of inference? Or can we say that weight of the father is more than that of the son? These types of things will come under the inference part. Again, come to the data. When you want to describe the data, we can just go for the descriptive statistics, whether the data is in attributes or it is in the variables. For attributes like gender of the person, you can just summarize the data in this form of frequency distribution table. We just divide the data into male and female and total number of persons. Just for an example, let us say we have 30 entries in our data, and out of the 30, 13 are male and 17 are female. Okay, this is for the attributes. And for the variables, you can again go for the different frequency distribution tables on the basis of the class in different classes, on the basis of the age group, on the basis of the weight, and different graphs can represent that. Data can be in attributes or it can be in variables, but you can just summarize the data in the form of a frequency distribution table. And then after summarization, we can go for different measures like measures of central tendency, just to get a single value, a single representative value of the data, or just use the measures of dispersion to supplement the measures of central tendency. As you know that measure of central tendency may not reveal the true nature of the data. Okay, this comes under the descriptive part, descriptive statistics. Okay. Similar techniques will be there for the bivariate data or multivariate data. Okay, so you can just describe the data in this form, but similarly for the bivariate data you can go for the correlation and regression, etc. But the questions may be different and statements may be different. For example, the statement could be more female than male undertake refresher courses. Just a decision sort of thing, or average weight of the persons attending classes is 65 kg, or is there any relation between the age of the father and his son and daughter? So look at the two statements and see the difference. Now we are discussing the inference part. Description, I suppose everybody knows, that is very simple thing, and you can represent the data into various descriptive measures. Now look at the statement. One may say more female than male attended the courses, or one may say more female than male attend the courses. Just look at these two statements. Okay. The first one is describing the complexion of the particular batch, whereas second is making a time and space free statement, a general statement. Right? You can see the difference. So again, come to the data. I'll just explaining each and everything by considering the same data. Let us say we just pick one variable. Let us consider the weight of the participants. Our focus is on the weight of the participants, one variable. Okay. Now, what type of statements, what type of questions we can have from this data? The first one which comes to our mind is, we can just check, could the average weight be said to be 65 kg? This is the question, and we want to get the answer of this question from the given data, from our data. Then the second case is, let us say we divide the data into the male and female participants, and can we say the weight of the male participants is same as the weight of the female participants? And the third thing is, same variable, just one variable, and see in how many directions you can exploit these variables. Weight of the participants. Suppose some treatment is given to the participants, and after that, maybe for the reduction of the weight and maybe for increasing the weight, and we can just check whether that treatment was effective or not. Data was collected before the treatment and after the treatment. So see, just one variable is there, and we can have three questions. We can frame three hypotheses, three questions, and get the decision on these things. Case 1, case 2, case 3. Right? This is just before and after treatment data. Now, I'll just give you small examples that how we can use this inference techniques. The basic things should be clear to you, that what is the purpose of this statistical inference. This is a very small example. Let us say keen observer computes that the average content in 10 bottles of soft drink, he collected the data of any soft drink brand A, 10 bottles, and found that the average content in these 10 bottles came out to be 295 ml with standard deviation of 5 ml. You see that when you look at the soft drink bottles, you can see that some variation is there in the content. Not all the bottles are having the same content. This variation is inherent in the process. Okay. So when he found this thing, that it is 295 ml with a standard deviation of 5 ml, he files a case against company on cheating. Why? Because company says this standard, the average content of the weight should be 300 ml and standard deviation is 10 ml. So in this case, the company wins the case because they justify their production saying that contents supplied are as per specifications. They have already mentioned that there must be some variation in the filling of these cans, and average content will come out to be 300 ml with a standard deviation of 10 ml, right? Similarly, let us say another person goes to the market and collects another data. Again, a sample of 10 bottles that may give average content of say 305 ml with a standard deviation of 5 ml. Now, in both the cases, company justifies that product is as per the specifications. Average content should be 300 ml and standard deviation is 10 ml. Now, why this variation? This variation could be due to cause and effect or by chance. If it is due to cause and effect, then it can be eliminated. But if it is by chance, this chance is due to sampling. You may be selecting different sample, I may be selecting different sample, and little bit variation will be there, and up to particular level that variation is acceptable. All these things we can test by using different statistical procedures, whether we should go for the rejection or we should go for the acceptance. The message is, based on sample observations, we take decision for the population totality. The sample may be small or may be large, but we take the decision for the big lot, the total. And the statistical analysis is carried out to draw inference about population on the basis of samples collected from the population. This is the message. Okay. Now let us consider another example. This is just a statistical, this is a genetic law. Very popular law is there. Even we can test this law statistically, whether this is correct or not. Everybody knows that a genetic law says that children having one parent of blood group M and the other parent of blood group N will always be one of the three blood groups M, M and N. And that the average number of children in these groups will be in the ratio of 1:2:1. Right? How to check this thing? We can test this thing also. This claim also can be tested. For example, let us say we collected the data on 162 children having one M parent and one N parent, and 28.4% were found to be of group M, 42% of group MN, and rest of the group N. Do this data conform to the expected genetic ratio 1:2:1? This is the question, and we can test it statistically. Statistical procedures are available to check this type of statement. Now the question comes that how to test? How to test this thing? All these statements are there, and how to go for the test? The answer of this question is very simple these days. Everybody will say that we go for T, F, and ANOVA. This is the answer. Everybody knows it. These names are very familiar. Of course, these are the basic tests, but we cannot use these tests in all the situations. We have to check the different assumptions, the data, and then we should go for these tests. Okay, what is t-test? This is very basic test, and everybody must be knowing about this test. The parametric test T. The test statistics is a t-test, and this is used to determine whether the population means differ. Whether you are going to test the single mean. I have just explained three types of the hypotheses or the statements from the variable weight of the participants. Where you want to check the weight of the single sample, you can go for the t-test. When you want to compare the weight of the two populations, two samples, you can go for the t-test for two independent samples. And when you just go for the paired samples, dependent samples, again there will be t-test available. So t-test is used in 3 categories at this thing when it comes to testing the mean of the variable. Okay? If we have more than 2 samples, 2 independent samples, let us say we want to compare 3 or more variables, the means of 3 or more variables, then we'll go for analysis of variance technique, one-way ANOVA. You must be knowing this thing. This is again a very popular test, one-way analysis of variance. And if the sample size is large, instead of t-test, we use z-test. Then for checking the variability, etc., for 1 sample and 2 sample, we'll be using chi-square and f-test. These are some of the popular tests which we are using, which everybody is using who is doing research. Okay. But here is the problem. You know about these tests, but how to select the right statistical test? In which situation, which test should be used? Just don't use these tests blindly. Just look at the assumptions, look at the different conditions, look at your data, the nature of the data, and then choose the right statistical test. Of course, using the test is not difficult. So many softwares are available, even on the net itself, Google itself. You just put that computation of the t-test, you will be getting so many sites, putting the data, you will be getting the value and the decision also. But where to use these tests, how to select the test, this is the problem. So choosing the right statistical test depends on nature of the data, sample characteristics, and inferences to be made. This nature of data is very important. Nature of only at that point only you decide about whether you should go for parametric test or non-parametric test. I suppose tomorrow there will be a lecture on non-parametric test. For the parametric test, we always go for normal distribution. The data, that sample you have, that should follow normal distribution. If it is not normal, you go for non-parametric test. Of course, that will be done in details tomorrow. So the first of all, for choosing a right statistical test, you have to look at the nature of the data. Then what are the sample characteristics? Once you know the distribution of the data, then what are the characteristics of that distribution? And then what type of inferences you want to make, whether you want to go for the inference about the mean, whether you want to go for the proportion, whether it is for the variance, and all these things that must be clear. Yeah. So let us just describe the fundamental terms. I suppose that everybody knows these things, but just to revise these things, the statistics and the parameters, then statistical hypothesis, then errors, and then test statistics. These are the 4 fundamental terms which are used in the inference. When it comes to the statistics, everybody knows that this word, when it is used in the plural sense, it is a data. When it is used in the singular sense, it is a subject. And then statistics is a formula or a number of formulas. Okay? And statistics in inference just represent the characteristics of the sample. You understand that there is a population which is very large, and we collect the sample from that population. We cannot collect the data for the whole population. We just select the sample and the characteristics of that sample. For example, you can compute the mean of that sample. For example, you can compute the variance of that sample. And if it is bivariate, accordingly, you can compute the different measures. And these mean and variances of the sample, they will be characteristics of the sample. So what is the difference between the statistics and parameters? The statistics are the sample characteristics, and parameters, they are the characteristics of the population, right? And you know that population is very large. It is unattainable. So the parameters are generally unknown. Of course, the sample characteristics, they are known. Sample is small. You can always compute these values, these statistics, they are known. But if you talk about the population, the parameters are unknown, but they are fixed. You know that what will be the parameter of this distribution. Once you can say that the distribution of the population is normal, you know that the parameters can be mu and sigma square. It will represent the whole distribution, right? So they are unknown, but they are fixed. Similarly, that value will be fixed, but sample values will be different. We can have so many samples. You may collect different sample, the other person may collect different sample. So the sample characteristics will be different. That will vary. That will vary from one sample to other sample. Okay? So the notation for these things, the population characteristics, they are denoted by the Greek letters. And the sample characteristics, they are with the Roman letters. For example, the population mean is denoted by mu. The population variance is denoted by the sigma square. But where if it comes to the sample, we just denote the mean by x bar and population standard deviation by s square. These are just the notations, just to distinguish between the population parameters and statistics. Then comes the term statistical hypothesis. How to frame the statistical hypothesis? Here, this is most of the statistical hypothesis concern about the parameters of the distribution. Most of the statistical hypothesis. To arrive at decisions about the parameters, we make certain assumptions about the characteristics, or we make a statement about a future event or about an event, the outcome of which is unknown, and we are open to reject the same. Right? The certain assumptions, the certain statements about the parameters of the population. Such assumptions or guesses, which may or may not be true, which can be actually tested statistically also, are called hypotheses. Right? So a statistical hypothesis is a statement, assumption about the distribution of a random variable, or it can be for the more distributions or more random variables. Okay. So this is a small example. See how many hypotheses can be framed out of this statement. We may say that the average age of employees in a factory is normally distributed with mean 32 years and standard deviation 10 years. We can just check all these things by collecting different data. The first hypothesis can be, the statement is given, the average age of employees is normally distributed. How to check this thing, whether it is normally distributed or not? Of course, this is a natural phenomena that the data follows normal distribution, but we have to check this thing statistically, whether it is normal or not. For example, if the sample size is very small, you cannot check the normality. The first hypothesis will be the distribution of the data is normal. This will be your first hypothesis, and this must be checked for any data before going for any other hypothesis. Because if it is normal, then there will be a different test. If it is not normal, then there will be a different test. And the second hypothesis can be testing the mean. This statement says that average age of the employees is having mean 32 years. So mean is equal to 32 years. This is another hypothesis, and the standard deviation is 10 years. This is another hypothesis. The sigma is equal to 10. So this is how you can frame the hypothesis from any data, from any given statement, right? So then one more thing, when you make the statement about the hypothesis, there will be always two types of hypothesis. Suppose you reject the statement, you reject the null hypothesis which you have just stated, then which one is to be, which one should be accepted? There should be some alternative. So the decision procedure is mainly concerned with the selection of either one of two courses of actions. And in testing procedure, attention is focused on two possible sets of values of the parameter or two statistical hypotheses. The hypotheses will always be in pairs. Such a pair of sets are called null hypothesis and alternative hypothesis. Right? In the case of absence of that null hypothesis, in case of the rejection of the null hypothesis, there should be some hypothesis which should be accepted. That will come under the alternative hypothesis. So the statement will be always in pairs, null hypothesis and alternative hypothesis. Then comes the concept of the how to denote these hypotheses. The null hypothesis is always denoted by H naught, and alternative you can denote it by HA or H1. If there are so many alternatives, then H1, H2, H3. So what we can do, we can just specify the conventionally the null hypothesis is specified in an exact manner, and it usually corresponds to the absence of effects of the variable being investigated. Whatever you want to check, the null hypothesis will always be a hypothesis of no difference. For example, look at this statement. Suppose we wish to decide whether one procedure is better than another. One is better than another, but what should be the null hypothesis? We formulate the hypothesis, the null hypothesis, such that hypothesis is the no difference hypothesis. The statement will be there is no difference between the procedures. So null hypothesis will always be a hypothesis of no difference. And whatever you want to check one procedure is better than another, that you can put under the alternative hypothesis. Right? Null hypothesis is framed in an exact manner. It is sharply framed. Again, there are statistical reasons why we frame the null hypothesis in the exact manner, because later on when you go for the different statistics, statistically you have to find out the distributions of that, and under the null hypothesis, because it is specified, the value of the parameter is specified, it will be easy to find out the distribution, etc. Okay, so always frame the null hypothesis in an exact manner, and whatever you want to check, that can be put under the alternative hypothesis. Okay, so this is regarding the hypothesis. One should be very careful in the framing of null and alternative hypothesis. Then comes the errors. Whatever procedures are applied for testing the hypothesis, there are always two types of errors. I'll just describe this quickly, because we have to do the different procedures also. Suppose sometimes what we can do, we know the null hypothesis is true, but still on the basis of our that information, we reject the null hypothesis. The evidences are like that. We are tempted to reject the null hypothesis, and sometimes what happens, the null hypothesis is false, and again our data is like that, our sample is like that, we are attracted to accept the null hypothesis. It means these are the errors. I think this has been explained in yesterday's lecture, so I will not waste much time. For example, this is just in a form of table, that the null hypothesis is true and we are accepting this is the correct statement. But the second one is null hypothesis is true, but you are rejecting the null hypothesis. This is called type 1 error. Then the null hypothesis is false and you are accepting this is type 2 error, and null hypothesis is false, you are rejecting this is correct statement. And if you look at these two things in testing of hypothesis, there are always two types of errors, type 1 error and type 2 error. The type 2 error is more dangerous, because here you are accepting a wrong thing, here you are rejecting a bad thing. A correct thing you are rejecting, but type 2 error is you are accepting a bad thing. So type 2 error is more dangerous. So in statistical inference, what we do, we try to minimize the risk of type 1 error. We try to fix type 1 error up to this much, it is tolerable, and try to minimize type 2 error. Okay, so this is the probability of type 1 error is denoted by alpha, and probability of type 2 error is denoted by beta. These probabilities are the risks of wrong decisions. All these things you know. Of course, we can reduce these errors by increasing the sample size, which is of course not always possible. So we have to make the balance. We have to just fix the risk of type 1 error and minimize the type 2 error. And generally this alpha, the probability of type 1 error, is known as level of significance, and it is denoted by alpha, and this is always pre-assigned, like it is taken to be 0.05 or 0.01. When we say 0.05, what it means? We are 95% confident that we are taking the right decision. 5% we may be wrong. When you see that it is at 5% level of significance, or alpha is 0.05, it means you may be wrong 5% of times. Out of 100, 5 times you may be wrong, but 95 you are correct. So this is the level of significance, definition of level of significance. And then you know that how to decide about the sample size. So many formulas are there. Confidence intervals are also there. Whenever you apply any test, you can find out the confidence interval also in which your value will lie. And then this is just alpha and beta. Means alpha is the level of significance and beta is the probability of type 2 error. And then what is the rejection region? There will be always a rejection region also, and this is referred to as the critical region, where if your value falls in that rejection region, you reject the null hypothesis. Okay, this depends upon your alpha, that how to get the critical region and the acceptance region. Okay, so this is again by the how you define the level of significance. When you say 1%, it means you are 99% confident in your decision making, which is very high. So normally we take at 5% level of significance, means we are 95% confident that we are correct in our decision, or we may be wrong with probability 0.05. Now come to the different testing situation. So these are the basic definitions which we must know before applying any test. As I told you that applying the test is not difficult. Computation of the test statistics is not difficult. The only thing is you have to look at the situation, which test is appropriate. Once you select the test, you have data, you just feed the data in any software, you will be getting values. Okay, now what are the testing situations? As I explained earlier also, the first thing is, the simplest thing is, if the sample mean differs significantly from a hypothetical value of the population mean mu, a single mean, testing a single mean. And the second is, if the given sample, this is the same thing, sample mean, or if the two sample means differ significantly or not, two independent sample means. Just we are focusing on testing the means. And third is if the population variance, and so many things, like you can consider more than two samples, you can consider the variability of the two samples and more also. Okay, these are the tests. Now what are the steps in testing procedures before applying any test? Suppose you decide about the test, what should be the steps? First of all, state the assumptions. This line is missing here. First of all, state the assumptions, like the population is normal, a sample is drawn from the normal population with known variance or unknown variance and all these things. Look at the assumptions, state the assumptions. The second thing is state a null hypothesis, and accordingly state an alternative hypothesis, right? Then define a test statistics along with the distribution of the test statistics under the null hypothesis. For this particular problem, which test should be used? Let us say we are going for one sample mean testing. We know t-test will be used. You have to define the test statistics theoretically. Of course, if we are just using the software, you have decided about the t-test and you just click on the t-test, you will be getting the value. But theoretically, define the test statistics, the formula of the test statistics. Then what will be the distribution of this test statistics? It follows t distributions with n minus 1 degrees of freedom, like that. Okay. Then compute the value of the test statistics from the information given in the sample data. Whatever information is with you, you just go for the mathematical computation of the test statistics. Then compare the calculated value of the test statistics with the theoretical value of the test statistics. Tabulated value, tables are available. If you are using t-test, t-tables are available. If you are using normal test, z-test, again the normal tables are available. If you are using chi-square test, chi-square tables are available. Okay, so theoretically you have to look at the tabulated values and compare your computed value with the tabulated values and decide about the rejection or the non-rejection of the null hypothesis. Of course, the level of significance is also there, which is predefined, right? This is your fourth step. Then this is the general procedure. These days we can go for the p values because every software gives you p value, but if you are applying it uh, theoretically, you are all doing all these things. If your calculated value of the test statistics is greater than the tabulated value of the test statistics, then usually the null hypothesis, which is the equality or no difference hypothesis, is rejected at the predefined level of significance. Okay, but if you are going for the p value, as it was explained yesterday also, if your p value comes out to be very small, like it is less than alpha 0.05, then you reject the null hypothesis. Look at the p value and take the decision. And your alternative hypothesis can be two-sided or one-sided. This also you know, because it was there in the yesterday's lecture. Okay, these are the steps in testing procedures. Now come to the t-test statistics. Okay, so the t-test statistics is regarding the means. Of course, it is used for the correlation, etc., correlation and regression coefficients also, and it was developed by the Gosset for the quality control of the pair. It was when it was developed, it was the basic thing was considered as quality control. Okay, and it comes in the three. If we talk about the mean, it is for the three things: a single sample, independent samples, and dependent samples. Of course, two independent samples and two dependent samples. Okay, so formula will be slightly different for the single sample, paired sample, and independent samples. Okay, so let us come to the this is we have explained. So let us come to again our original data. Let us say we want to check whether the average weight of the employees is 65, average weight of the group of persons, group of students is 65 kg or not. This is our question and we want to get the answer of this. So first of all, we look at the assumptions. This is the data on that variable weight. Look at the distribution, whether if it is normal distribution, it will take this type of shape. And of course, some tests are also there, which is known as non-parametric tests for testing the distribution, also known as goodness of fit tests. Okay, you can check the distribution of the data. This is the first step. Look at the assumptions, normality of the data. And what about if any variable is that any parameter is specified, like variance is known or variance is unknown. Okay, then what will be the null hypothesis? The assumptions we have checked. Now what just remember the testing procedures. Explain the null hypothesis, state the null hypothesis. Mu is equal to 65 kg. We want to check this thing. This is mu. Mu is equal to 65 kg and alternative is mu is greater than 65 kg. Or the alternative can be mu is less than 65 kg. And a two-sided alternative is mu is not equal to 65, right? You can select any of the three alternatives depending upon your problem, your set of problems. Then look at the level of significance. Now hypothesis is defined, alternative hypothesis is defined. Let us say it is two-sided, mu is not equal to 65. Then what is the level of significance? What was the level of significance as per your given conditions? If it is 0.05 or 0.01, then test statistics, just state the test statistics, and of course in this situation t-test is used. Okay, And then if it comes to our focus is on the two independent samples, weight of the female participants and weight of the male participants. How to state the null hypothesis in this particular situation? Of course, we have to check the assumptions also. Here the assumptions will be whether they follow normal distribution or not independently. This should also follow normal distribution. This should also follow normal distribution. Okay. And the null hypothesis will be stated that mu f is equal to mu m, means weight of the female participants is same as the weight of the male participants. The null hypothesis of no difference. And alternative is, let us say they are not equal, or you can put that female participants are having less weight than the male participants, or vice versa. Depending upon the situation, you can state the hypothesis, alternative hypothesis. Then look at the level of significance test statistics, and here the test statistics which is used is known as t-test for two independent samples. Okay. And the third case will be the same data set is there, the variable, the weights of the participants, and then after the treatment the weights are again recorded, and we want to check the whether that treatment is effective or not, whether the weights before and after treatment are different or same. So three situations, in all the three situations we'll be using t-test. Of course, a little difference in all these formulas. And the last case, in the paired sample, the null hypothesis will be that the mean of the difference mu d is equal to 0. Mean of the difference. Here the dependent samples are there, paired samples are there, or dependent samples you can say, or the repeated measures are there. Okay, on the same person, the observations are taken repeatedly. Okay, so mu d is equal to 0, and alternative is this is not equal to 0. And of course, the level of significance, then test statistics are here. The test statistics will be used as known as paired t-test. Okay, for the, of course, for the two dependent samples. So let us consider a simple example, and I'll explain that how to use the t-test in this case. Okay. The only thing is you have to guess that in this situation we have to use the t-test, and accordingly you can use different that softwares to compute these values. But those who want to check the formula, here it is given. Let us see, our aim is to check the mean cholesterol hypertensive man. What is the mean cholesterol in the hypertensive man? Mean cholesterol in male general population is 20 to 74 years old. Okay. And it was stated that the mean cholesterol level should be 211 ml with the standard deviation of 46 mg/ml. Okay, so we want to check this statement whether this is true or not. This is the you can say already given statement. This type of situation is there, and we want to check it statistically whether this is correct or not. So data is there, and on the basis of that data, that mean, and of course the data was collected on all these hypertensive men, the cholesterol level of these hypertensive men. But in this case, the null hypothesis will be stated as that mu is equal to 211, means mu is population mean serum cholesterol for male hypertensive. Okay, mean for general male population. And alternative is it is not. It may be smaller than this, or it may be bigger than this. Accordingly, whatever is your problem, you can frame the alternative hypothesis accordingly. Now for this type of hypothesis, because nothing else is given, only the thing is the normality of the data and the variance is unknown. Variance of the population is unknown, and this is of course continuous outcome. Unknown variance is there. Under H naught, the test statistics will be used as x bar minus mu naught upon s upon under root of n. Mu naught is the value of the mean which is computed from the sample which you have collected. Okay. So mu naught value will be put from that. S is also computed. S is the standard deviation from these sample values, and n is the sample size. Now this test statistics, the distribution of the test statistics under the null hypothesis, because this value is taken under the null hypothesis. So this follows t distribution with n minus 1 degrees of freedom, right? Then after the computation of these values, either you compute the p-value or from the software you notice the p-value. If you have computed it manually, then go for the critical values. So just open any statistics book or from the computer. According to the different degrees of freedom, you will be getting the t-value. And if the sample size is bigger than 30, t values are available up to n is equal to 30, less than equal to 30. And if your sample size is bigger than 30, you can use the normal table, normal distribution table. This t will be approximately normal for degrees of freedom which are bigger than 30, and you take the decision. So let us just say that for one data, you have collected the data on, let us say, 25 persons. The hypertensive males were there and their cholesterol level was noted, and X bar came out to be 220 and the standard deviation came out to be 38.6, and the value of t comes out to be 1.17. And let us take the level of significance is 0.05, 5% level of significance, and two-sided this test. This is two-sided test, two-sided alternative is there. The critical value from the table with n minus 1 degrees of freedom means 24 degrees of freedom comes out to be 2.064. So the computed value is smaller than the calculated, this tabulated value. So what is the decision? We should not reject the null hypothesis. If your computed value is bigger than the tabulated value, then you reject the null hypothesis. The difference is not statistically significant at 5% level of significance. So here we fail to reject the null hypothesis. These are the proper procedure to go for any test. Okay. So if you compute this value, if you apply the t-test from the by using any software, then you will be getting the p-value. Look at the p-value. If p-value comes out to be less than 0.05, you reject the null hypothesis. If p-value is bigger than 0.05, then you don't reject the null hypothesis. So here definitely p-value will come out to be more than 0.05. You just compute t-test from using any software or just searching on the Google computation of the t-test, you will be getting these values. But you have to decide that in this particular situation, we have to use the t-test. In the absence of t-test, suppose normality is not there, there will be a non-parametric test. So these non-parametric tests will be explained, I think, tomorrow. So then the confidence interval also you can find. This is the formula for the confidence intervals. The tabulated values, the mean is there, that mean is from the sample. You have to subtract this expression for the lower value and add this expression for the upper value. The confidence interval comes out to be 204.06 to 235.93. So definitely the value which it was assumed 220, this falls in this. Okay. So we can accept the null hypothesis. So paired the thing is there again, the two continuous outcomes are there. If the variances are known, population size is large, we go for the Z test statistics. But unknown variance, we go for T test statistics. And the null hypothesis is that mu D is equal to 0 versus mu D is not equal to 0. Means the treatment is not effective. When you say that after the treatment mean comes out to be same, mean weight comes out to be same, it means treatment is not effective. And when you say mu D is not equal to 0, it means it is effective. Whether the weight increases or decreases, that will come under the one-sided alternative. You can put mu D is greater than 0, mu D less than 0, like that. And this is the test statistics. If variance is known, you can just put sigma. D bar is the mean of the differences of the weights, and compute S if sigma is unknown. This is for T test. Okay, so this is a simple formula, and just on the basis of this Then you have two independent samples. I'll just concentrating on the t-test here only. The unpaired test means independent samples, variance is known variance, that test statistics will be there. Sample size large है, variance पता है आपको, तो you go for Z test statistics. But if unknown variance and the sample size is smaller than 30, you go for T test statistics. And of course, normality of both the populations are there. The independent populations, the independent samples are there. Okay, so the null hypothesis is that mu1 is equal to mu2. The means are equal, and versus mu1 is not equal to mu2. So assume common variance. Assume common variance of, again, it can be common variance also, uncommon variance also. Both these formulas are there. Whatever is your assumption, you can use that. So this is Z test statistics when sigma is known, common variance is known, and this is S, which is computed from the observations. Okay. So this is like that test statistics. And then regarding the mean, testing of mean, the last thing is ANOVA. If you are interested in testing the means only, if we want to compare the means of more than two samples, more than two independent samples, then this comes under the analysis of variance, right? For example, our focus is in the weight of the four types of participants. Let us say it can be more. It should be more than two. Focus on the four types of participants, and we want to just check the means of all these four samples is same or not. Okay, so this is called one-way ANOVA. And what are the basic assumptions for one-way ANOVA? One-way analysis of variance is used when we have a categorical independent variables with two or more categories. For the two, we have t-test. For more than two categories, we have ANOVA. And of course, these variables, they are normally distributed. The assumption of normality is always there for using parametric tests. Okay, and we wish to test for the differences in the means. Okay. So in this case, the null hypothesis will be stated as mu1 is equal to mu2 is equal to mu3 is equal to mu4. Suppose we have four groups of participants, and alternative is not all mu's are equal, not all means are equal. Okay, right? So this is regarding the testing of mean. Similarly, we can go for testing for the variance, single variance also. Testing the variability is equally important. So if you permit, then I can go for that. But I think time is up now. Where is Dr. Tiwari?
Yes, ma'am.
Should
Yes.
we continue? Anji, just have a variability test, and that is there. F and
No
chi-square. If you
no
want me to
problem.
continue, I can continue.
Yeah, no problem, ma'am. We have time. If it,
Okay.
we have time.
Okay. Yeah. And participants also, if you have any query regarding the testing of means, you can just ask.
Please, I allowed everyone to unmute at their end. If have any doubt, then please clarify your doubts. Yeah.
Yeah, please. And explain the testing of variability also. Okay. Because when you go for the assumption that this is normally distributed, population is normally distributed, and then definitely the variance of the normal population is also there, and you can check that also. So F test is when you just check the variability of the two populations. Variability of the two populations. Of course, single population, I think that will be afterwards. So let me just, yeah, this is there. Yeah. So this is the packing machine is this regarding the variability of the packing machines of some meal bags, let us say. Okay. You know that when if you go to any industry, you can see that not all the uh, contents are same. Okay. So let us say this is a small example. Why do we need to check the variability? Suppose people have lodged complaints about the weight of a 12.5 kg milli meal bags. The complaint was that the bags they are having not having the specified weight in the bags. They are underweight or whatever the complaint was there. So what then the quality control manager, what he did, he took a sample of milli meal bags and did not find any problem with the average weight. जब उसका एवरेज लिया गया तो उसको लगा कि कोई प्रॉब्लम ही नहीं है. So that she could not reject the hypothesis that the population mean weight is 12.5. अगर मीन को चेक किया गया तो देयर वाज नो प्रॉब्लम, बट स्टिल द कंप्लेंट वाज देयर दैट देयर इज a different type of weights are there, the variation. What was the problem then? What could be the problem? The problem is regarding the variability is different. Variability was very high. Average to same आ गया. Average will be same if let us say in one the item the weight is quite high, in the other item weight is quite less. The average will come out to be same, but definitely where the weight is less, that will not be accepted in the market. So here testing of weight is not advisable. Although the mean is okay in the above example, there could be a problem with the variance. Packaging plants are designed to operate within certain specified precision. कुछ उसमें स्पेसिफाइड लिमिट्स होती हैं कि वेरिएशन शुड नॉट इंक्रीज फ्रॉम दिस. जैसे मैंने बिगिनिंग में एक एग्जांपल लिया था, द स्पेसिफिकेशन वाज दैट एवरेज कंटेंट शुड बी 300 ml विद ए स्टैंडर्ड डिवीजन ऑफ 5 ml. Up to 5 ml the weightage is that 10 ml. Up to 10 ml the variability is acceptable, but not more than that, right? So in this case the variability was high, so that was rejected in the market, and every time the quality control manager was saying that no, it is according to the specifications, because he was just checking the average content of the wheat. Okay, so ideally it will be desirable to have the machine pack exactly 12.5 kg in every bag, but this is practically impossible. So a certain pre-specified variation is tolerated. This is important. Okay, so we can check the variability in the data. Okay. So, and one more thing, suppose one machine is there which is packaging the material, but after a certain time, when it starts packing, some error comes. Again, the variation will be there. So you know that every time they set the that machines so that there should not be variation in the precision of the packaging. Okay, so it means here we need to test the hypothesis that sigma square is equal to sigma naught square. How much variation is acceptable? That will be under the null hypothesis. But if variation comes out to be less than this, then definitely there is no problem. But if it comes more, then the hypothesis should be rejected. So alternative is sigma square is greater than sigma naught square. Here this type of alternative will work only. You cannot say sigma square is not equal to the sigma naught square. That should be the alternative. No. Because when it is less than sigma naught square, it will be accepted. It will be acceptable in the market. The company wanted to just look at the problem. What is the problem? That why the complaints are there? Okay, so they check the variability. Whatever variability is specified by the company, that was put under the null hypothesis, and if it comes out to be more than that specified value, then the hypothesis was rejected, right? So similarly, if let us say ये one sample problem है, this is one sample problem. Let us say there are two machines. Any factory, any industry, they want to buy one machine. Which machine they will prefer? Which will give the less variability? Packaging machines हैं, दो packaging machines हैं plant में, and just a company, a factory wants to buy a packaging machine. He is not sure he should go for machine A or machine B. Now the variability in the two machines is compared. Sigma A square is equal to sigma B square. He will prefer the machine which will give the less variability. Okay, and the sample variance during these two machines come out to be SA square, while machine B produced sample variance SB square. And our question is, are these variances significantly different? Now I think the concept of testing variability is clear. We'll prefer the sample, we'll prefer the product which will give us the less variability. Less variation is always acceptable, whether we are talking about one machine or two machines. When it is regarding one machine, so if you check whether the variability is as per the specification limits or not. If it is high, go for the rejection. And similarly for two machines, check the variability and prefer that machine which gives us the less variability. So in the two sample variability test, two variances test, we go for the F test, and in one sample variability test, we go for chi-square test. You must have heard about chi-square distribution and F distribution. F distribution is nothing but the ratio of two chi-square distribution. Okay, so this is just the two sample problem. This is the weights of the millimole bags packaged from machine A and AB respectively. So null hypothesis is sigma A square is equal to sigma B square against the alternative that sigma A square is not equal to sigma B square. So this is regarding the two sample. But now come to the one sample. Of so many examples are there, because every time you control the variability in the market, also in the foreign exchange, stability is important, price stability is also important. So just they want to control the variability. So when it is one sample, the chi-square test will be used, and the null hypothesis will be that sigma square is equal to sigma naught square, and the alternative is sigma square is greater than sigma naught square. And the test is based on the comparison between the sample variance and the population variance using this ratio. This is the test statistics. Look at the test statistics. Theoretically, those who want to see, this is the formula, which is not very difficult, n minus 1 s square upon sigma naught square. This is given under the null hypothesis, and s square you have to compute from the given data. Okay, so calculate this value and look at the tabulated value with n minus 1 degrees of freedom from the chi-square table. Okay, and similarly you can compute the p-value also. Either you compare this computed value with the tabulated value, and testing procedure will be same. If your computed value is smaller than the tabulated value, you accept the null hypothesis, otherwise you reject the null hypothesis. Similarly, this is the p-value, computation of the p-value. If your p-value comes out to be less than 0.05, you reject the null hypothesis, otherwise you accept the null hypothesis. This is regarding the chi-square distribution, and this is positively skewed distribution, and this shaded area is the p-value. This represents the p. If your p-value falls here, you reject the null hypothesis. Okay, this is the example. Same example is there. Millimole packaging machine, and sigma naught square, which they want to check, is that 0.0016 kg. And suppose the data from the sample of 12 millimole bags gave this much variation, 0.0025 kg. Let us see whether this difference is significant or not. Does the data indicate a significant increase in the variation? So this is the test statistics, n minus 1 s square upon sigma naught square. 12 bags were there. So this is 11 into that s square, the value of s square and sigma naught square, it comes out to be 17.2, and the p-value based on a chi-square with 11 degrees of freedom comes out to be 0.143. So what this means, p-value is bigger than 0.05, it means you are not rejecting the null hypothesis. No significant increase in the variation is there. That sample, that data, that product should be acceptable in the market. That complaint is invalid, right? The variation is as per the specification limits. This is how you interpret the data, how you interpret your hypothesis. The variation is found to be as per the specification limits. So we should not reject the null hypothesis. We should not reject the lot. Similarly, this is for the two-sided. Sigma A square is equal to sigma B square. When you just comparing the two variances, the variability of the two machines, sigma A square is equal to sigma B square, and alternative is the variation in A is more than the variation in B, and variation in A is smaller than the variation B. So here that machine will be accepted where the variation is smaller. Or the two-sided alternative. Here, of course, two-sided will not work because the person has to choose one machine. Okay, so this is the test statistics. These things you can see from anywhere, the standard things. The only thing is you should know the applications of these, the utility of these test statistics, where to use which statistics, that is important. Okay, so this follows F distribution with n1 minus 1 and n2 minus 1 degrees of freedom. Sample A है तो na minus 1, sample B में nb minus 1 degrees of freedom. Okay, ये F statistics है. And this is again a small example is given. 20 items produced on test trial of machine A gives this much variation, while 20 here it is not necessary कि आपके दोनों sample sizes same होंगे. Sample sizes may be different. From the first sample only 20 items were selected, from the second sample 27 items were selected, and they gave the variation as 0.0016. And our question is, does the data provide evidence that the working precision of the two machines are significantly different? Right? So value of that F statistics comes out to be 2.99. I am not sure about the p value is 0.01. या ये स्टैटिस्टिक मैंने किसी सॉफ्टवेयर में डाल के निकाली है p value. This comes out to be 0.01. This indicate a significant difference in the variance. तो दोनों machines में significant difference है, तो definitely we will go for the machine which is having less variability. And one more thing, I am talking about the statistical softwares. The these days so many softwares are available, but the most popular software is the SPSS. That is of course very costly, but the sample versions are free downloading is available, and the students, they just manage that thing and just put your data on that, and whatever test you want to use, select that variable, go for that hypothesis and get the result. That is very easy software, menu driven software hai, so SPSS is the most popular software. Okay, so this is all about, of course so many more tests are there. I just concentrated on mean and variances. Okay, proportions के टेस्ट भी होंगे, correlation bivariate में आएंगे, correlation and regression के टेस्ट भी होंगे. So but only thing is, once the basic concept is clear, then you can use any test. There is no need for going into the detail of the mathematical things, the formula, etc. Select the test, look at the assumptions, and go for the results. Right? So this is all. I hope it was very late, but I started late, I suppose. Okay. And if you have still any doubt, I can discuss. You are open to discuss this?
Yeah, all delegates are requested, if having any doubt regarding today's session on parametric test, please clarify your doubts within 2 minutes, so we will bind up the session. Thank you, Dr. Maqsood Ahmed, for positive feedback. If any doubt, then please either unmute yourself, ask the query, or simply write in the chat box. Use any method.
Thank you so much. But still you are open to ask if there is any doubt, and if you want to ask me personally, you can ask. You can
Yeah,
have my
definitely.
number, and because
Yes. All delegates are, if having any doubt later, you can just mail us. We will contact with ma'am and will share you the answer. So thank you everyone for positive feedback in the chat box. I hope everything is clear. I will share the recording of the session also. So if anything missed, you can revise going back, and I will share the PDF files also with the after receiving with ma'am tomorrow. So thank you, ma'am, for delivering a wonderful and a very detailed session on parametric test. I hope it will enhance the quality of the program, and all delegates joining from different institutions will benefit from this session. So on the behalf of organizer, I convey our sincere gratitude to our respected resource person, Dr. Kalpana ma'am, for delivering a wonderful session. Thank you, ma'am. Thank you for your valuable time and
thank you so much.
expertise.
Thank you so much. Thank you.
So all delegates, as scheduled, tomorrow we're moving toward the third part of non-parametric test that will be delivered by Dr. Anup Kumar sir, Associate Professor from the Department of Biostatistics, SGPGI, Lucknow. So be on time. Tomorrow's session will start at scheduled at 7:30 p.m. Thank you everyone. This is the end of today's session. Thank you for
Thank you.
joining.
Thank you.
Thank you, ma'am. Thank you, ma'am.